So in this video, we're going to go over basic circuits, so series circuits and parallel circuits, and we'll touch on a little bit of combination circuits. These are some of the most common circuit diagram symbols that we'll use in this class. The main ones that we'll see today are batteries, wires, resistors, and light bulbs. Occasionally, I will draw ammeters and voltmeters. And when I draw ammeters and voltmeters, I would like you to take note of how they're connected to the circuit. There are two types of circuit connections: parallel circuits and series circuits. These are the basic kind of connections that we can have, and we can combine them as well into combination circuits. A series circuit is a single path from the battery through a device or a resistor, directly through another device or resistor, and back to the battery. We can also have multiple resistors in series. So we can have, this one has 2 resistors. We could have 3, 4, 5, 6, 7, as many resistors as we want in series. Parallel circuits have multiple paths. In series, there's only one path we can take, and we have to go through every single resistor. In parallel, we go from the battery, and then at some point we come to a junction where we have to make a choice. And how the choice is drawn will depend on just the way it's drawn. We can draw it like this, where we come to a junction and we have to go up, down, or forward. We can also draw it like this, where we just go up or sideways, up or sideways. Both of these are valid ways to draw parallel circuits. The mnemonic device that I use to help students remember which is which is with a TV series and parallel universe. So in series, we have to go one right after the other. Same thing for a TV series. If you're binge watching a TV series, you're watching one episode right after the other, after the other, after the other. In parallel, I like to think of it as kind of like parallel universe. We have multiple paths with multiple outcomes happening at the same time. The properties of series and parallel circuits are different. So in both of these, we have 7 light bulbs connected to each other, but in the first case, we have 7 light bulbs connected in series, and in the bottom case, we have 7 light bulbs connected in parallel. In series, what happens to the rest of the lights if just one light breaks? And in parallel, what happens to the lights? We need to keep in mind that there are 3 things that we need for a circuit, for a successful circuit. First is a power source, which we have in both cases. The second is some device that draws the current. In this case, it's light bulbs, but it could also be resistors or fans or cell phones. The third thing we need is a complete circuit. So we can't have any breaks. There has to be a way for the electrons or the current to go into the circuit, and there has to be a way for the electrons to come out of the circuit without any gaps. In series, when one light bulb breaks, it creates a gap in the circuit. So in series, If we go from the outlet or the wall or the battery, the electrons could travel that far, but then there's a break. And because there's a break, none of the light bulbs will light. Even though electrons, so a lot of students will say, oh, these will light and these will turn off, or vice versa, these will light and those will turn off. But that's not the case. If the circuit is not complete, then none of the electrons can move. In parallel, what happens? We have the same 7 light bulbs connected, but now they're connected in parallel. Will the others stay on? Will just some of them stay on, or will they all turn off? In parallel, there are multiple branches, almost like having other little circuits, and the electrons can go from the battery and back through the light bulb and back to the battery without coming across a break. And even these far light bulbs, they can reach. So in a parallel circuit, all will stay lit. On this slide, we have 2 different combination circuits, but we're changing which light bulb is broken in each circuit. So number 1 and number 2 are the same circuit, but we're switching which light bulb breaks. And number 3 and number 4 are also the same circuit, and we're seeing which one breaks. In the first circuit, how are these 2 light bulbs connected? Are those 2 light bulbs connected in series, which means we have to go through both? Or are they connected in parallel, which means we have a choice? In circuit number 1, these 2 light bulbs are connected in parallel. If we go through the battery, ignoring that this light bulb's broken right now, when we get to this point, we have a junction and we have to choose whether we go to the left or to the right. How is the single broken light bulb connected to this parallel group? The single broken light bulb is connected in series to the parallel group. If we go through the light bulb, or we have to go through the light bulb to get through to the parallel group, or if we go through the parallel group this way, we still have to go through this light bulb to get back to the battery. So that single light bulb is connected in series. What will happen to the other 2 light bulbs when that one light bulb breaks? In this case, all light bulbs will turn off. In circuit number 2, it's the same configuration. We have a parallel group connected in series to a single light bulb and then connected to the battery. But this time, one of the light bulbs in the parallel group is broken. What will happen to the other 2 lights? In this case, because the electrons can avoid the broken light bulb and return to the battery, all of the light bulbs will remain lit. In circuit number 3, how are these 2 light bulbs connected? Are these 2 light bulbs connected in series, or are they connected in parallel? These two light bulbs are connected in series with each other. If we go down this branch, we have to go through both light bulbs. So if we don't have a choice, they are in series with each other. How is the single light bulb on the left connected to the series group on the right? Are they connected in parallel with each other, or are they connected in series with each other? This light bulb is connected in parallel with the series group. So if that single parallel light bulb breaks, what will happen to the series group? Will both lights stay lit, or will they both turn off, or will one do one thing and the other do another thing? In this case, all stay on. And in my class, it is okay to assume that by saying all stay on, that you're not including the broken light bulb. The broken light bulb will not be on, but all of the others will stay on. And that's because they can avoid the broken light bulb and still return to the battery. In circuit number 4, we still have the same connection. We have a series group connected in parallel to a single light bulb, but this time we have one of the series light bulbs broken. What will happen to the other two light bulbs? In this case, one light bulb does one thing and the other light bulb does another thing. This light bulb will turn off and this light bulb will stay on. And that's because for the light bulb that's in series with the broken light bulb, the electrons can't get past the broken light bulb, so they won't flow through that branch. But the electrons could flow through the other branch, and so that light bulb will stay on. This is a bit like how Christmas lights are wired. If one light bulb in a string of Christmas lights breaks or goes bad or is missing, then a section of the lights will turn off, but not all of the lights. I like to use an obstacle course comparison a lot of times when dealing with circuits because I think it's very useful for students. In this case, the current is the amount of runners, the resistance is the difficulty of the obstacles, the voltage is like the stamina of the runners, and the battery is like the bed where you can go and rest and get ready for the next race. For series circuits and parallel circuits, just like we saw how the properties of series and parallel circuits change depending on how they're wired together, we also need to take into account that some of the calculations that we will need to do will change depending on whether we have a series circuit or a parallel circuit. In series, the resistance is added together, which means the race for the electrons gets harder and harder as we add more obstacles. The equivalent resistance is the amount of resistance a single resistor would need to have in order to replace the other resistors. So in my picture below, we have 9 different obstacles. And the obstacle course is going to be a certain amount of difficulty. If we wanted to find the equivalent resistance, that would be like saying, how difficult would one obstacle need to be in order to replace all of these other obstacles? It can sometimes be called total resistance, but there's a slight difference Sometimes it's not just straight up adding things together. In parallel, we won't just add. There's a little bit of a trick to it. In series, the current stays the same, which means we don't lose any runners in the race. If we have 14 runners start the race, 14 runners have to go through this obstacle, 14 runners through this one, 14 runners through this one, and then we have to have all 14 runners come out the other side. The voltage, and remember, think of that like stamina, or kind of energy, but energy is also a physics word, so I try to avoid it when it comes to circuits. The stamina in the electrons is going to decrease as you go along. So if you have 9 different obstacles that you know you need to go through, you're not going to use all of your energy for the very first obstacle. You're going to save some of your energy so that you can finish the race. Now keep in mind that for current and voltage, these two equations are not very useful for calculations. They're useful to us in a lot of different ways, but they're not useful for solving for something per se. You'll see why on the next, when we start solving. We'll have to use Ohm's law instead. So when we're solving for current, Ohm's law looks like voltage divided by resistance. And when we're solving for voltage, that looks like current times resistance. This equation is also useful for checking our other calculations. So let's see what that looks like in this circuit. We have a 4 ohm resistor, a 6 ohm resistor, and a 12 ohm resistor connected in series with a 24 volt battery. And how that's drawn can be different ways. So we can have them lined up one right after the other. We can also draw them on different sides of the circuit, but both of these are connected in series because we don't have any choices. No matter what, we have to go through all 3 resistors in order to go back to the battery. I'm going to draw it the long way down here so we have some space to write some information. What is the equivalent resistance in this circuit? Since we're in series, we just add the resistances together. So 4 plus 6 plus 12. 4 plus 6 is 10. 10 plus 12 is 22 ohms. So the equivalent resistance in this circuit is 22 ohms. What is the current in this circuit? And like I said on the previous slide, current remains the same throughout the circuit, but that's not useful for information for solving in this situation. So in order to solve for the current, we need to take the voltage of the circuit and divide by the resistance of the circuit. The voltage in the whole circuit is 24, and the resistance in the whole circuit is 22. And we get the answer 1.0909090909, and it keeps on going. Don't be afraid of having repeating answers or even irrational answers. That can happen quite often in circuits. What is the current and voltage across each resistor? Once we get to the point of looking at each resistor, we need to ask ourselves a very important question, And that question is, what stays the same in this kind of circuit? In series, the thing that stays the same is the current, which means the amount of we don't need to solve for the current. So like I said, the equation is not useful for solving, but it is useful in the sense that now we know that all of the circuits, all of the resistors have a current of 1.09 amps. And if we put an ammeter in this circuit, we connected an ammeter at any point in this circuit, it would tell us 1.09 amps. For the voltage, we need to solve. So voltage equals current times resistance. We're going to have to do that for each resistor. So each resistor is going to have the same current because we're in series. So the current through resistor 1, and I'm going to call this 1, 2, and 3 over here. The current through resistor 1 is 1.09 amps, and the voltage through, or the resistance of resistor 1 is 4, so we get an answer of 4.36 volts. For resistor 2, current times resistance again, 1.09 amps of current because current stays the same in series, and 6 ohms of resistance for that resistor. So we get 6.55 volts. For the third resistor, it has the same current as the other two because we're still in series, 1.09 amps, and it has a resistance of 12 ohms, so the voltage drop across that resistor is 13.09 volts. How do we check this answer? All three of these should add up to the total voltage. They should add up to 24 volts, and they do. If you ever add them up and they're all of a sudden they're not adding up properly, you can make a note sometimes to yourself and be like, oh, I need to come back to this and I need to double check. Sometimes you won't have the time to, so you might want to make a note. Like, especially if it's a written out problem, you can say, these should add up to 24 volts, and they're not, right? And then I know that you know that there's a mistake in your mathematics somewhere. So the algebra went wrong somewhere, but you know the physics better than the math is showing me. I made a mistake the other day. I flipped around these. I did 22 divided by 24. And I did the check and it didn't add up to 24, but I didn't have time during class to go through and stare at it and look at where I had gone wrong. For the same reason, I didn't have the time. For parallel circuits, resistance is added inversely. And that can be a little tricky for students because, for example, say you can have 1 over R plus 1 over R, and you get the answer of 0.33. 0.33 is not your final answer. 0.33 is 1 divided by the total. So you need to take the inverse again in order to get the correct answer, and you'll see that when we do our example. In this case, current is split. Current is different in parallel. So if we have 14 runners start the race, they can choose which path to go down. So we might have 7 runners go through the top branch, we might have 3 runners go through the middle branch, and 4 runners go through the bottom branch. But if you notice, all of these should still add up to 14 runners. We shouldn't lose any of our runners as we go along, and then as they come out, there should still be 14 runners. In this case, voltage is the same, and that's because especially when there's only one obstacle on each branch, and then you get to go home at the end of the race, just after going through that one obstacle, you are going to use all of your energy, all of your stamina in order to go through that one obstacle, no matter which branch you go down. So all of these, you should use all of your energy to go through those obstacles. Again, these are good for checking, especially for current. This is good for checking the calculations. And knowing that the voltage is all the same will be useful for filling in all of the information. So, since we are adding fractions, please use a calculator for this. Sometimes you'll be able to do it in your head, but please use a calculator if you're unsure. Adding fractions is not the same as adding numbers. For example, if you have a 6 ohm resistor and a 12 ohm resistor wired in parallel, what is the equivalent resistance of these two resistors? We have to take, when you're adding fractions, you have to have common denominators. So 1 over 6 plus 1 over 12 is not 1 over 18. What you would have to do is turn this into 2 over 12, which would get us the answer of 3 over 12, but that's still not very useful. 3 over 12 is not very useful to us. If you put that into your calculator, it will give you the number of 0.25. And there's for many calculators, especially the TI-84 calculators, there's a button that does this for you. So rather than typing 1 divided by 6 plus 1 divided by 12, there's a button that has x to the negative 1, or if it's a simple scientific calculator, it might have 1 over x, and that makes it so much easier, because then all you have to type is 6, press the button, and on a graphing calculator it'll put a negative 1 next to it. And then 12, press the button, it'll put a negative 1 next to it. Press enter and you get 0.25. But like I said, this is not our final answer. We need to either do 1 divided by 0.25 or 0.25 to the negative 1, and that will get us the proper answer. And one more thing, so what's 0.25 in a fraction? Because this one you can do in your head. 0.25 in a fraction is 1 over 4. So these answers, so our full answer is 4. Let's do that again with a full problem. Notice this is the same 3 resistors at this time and the same battery, but this time they're connected in parallel. what is the equivalent resistance of the circuit? So we have the equivalent resistance equals 1 over 4 plus 1 over 6 plus 1 over 12. And if you plug those into the calculator, it comes out as 0.5. But remember, let me draw the circuit. Let's get to drawing the circuit first. So like I said, we can have a couple different ways of having parallel circuits drawn. We can have just boxes. We can have the parallel part 2, 3. There's 3 resistors, so 3 little branches, and then they're connected this way. Both of those are the same. We could also turn them horizontally or upside down if we wanted. Back to the resistance. So 0.5 as a fraction is 1/2. So we know 1 over the equivalent resistance equals 1/2. This one you can do in your head. It's a little easy to ask yourself, oh, what fraction is this? Sometimes that won't be the case. A lot of times that won't be the case. Don't be afraid. Use the calculator. I encourage you to use the calculator for this. So that means our equivalent resistance is 2 ohms. What about the current in the circuit? So in this case, we still have to, for the entire circuit, we still need to calculate the current. So current equals voltage divided by resistance. The voltage for the whole circuit is 24, and the resistance for the whole circuit this time is 2. So our current this time is 12 amps. And that would only be true if we measure it down here near the battery, or somewhere before these junctions. Now, what is the current and voltage across each resistor? And remember, when we're asking ourselves about each resistor, we need to ask what stays the same in this circuit. In parallel, the thing that stays the same is the voltage across each branch. So in this case, each branch has a voltage of 24 volts. So if we measured across each branch, and voltage is measured around something, so to measure current, we stick the ammeter directly into the circuit. To measure voltage, we stick it around whatever we're trying to measure. In this case, we're just measuring each branch. So now we need to calculate the current. So current is going to be different. Current equals voltage divided by resistance. And we have to do that for each resistor. The voltage across the first resistor is 24 because we're in parallel and the voltage will remain the same. And the resistance is 4, so we get 6 amps of current. The next one still has 24 volts and it has 6 ohms of resistance, so this has 4 amps of current. And this one has 24 volts divided by 12 ohms of resistance, so we get 2 amps of current. And the way to check those is that they should add to total current. And they do. Our total current is 12 amps, and they add up to 12 amps. Another way to check is to see, do most of the electrons take the path of least resistance? And they do. The less resistance one branch has, the more electrons are going to try to go down that branch. The higher the resistance in that branch, the fewer electrons will go down that branch. Remember, current is kind of like the amount of runners in that part of the circuit. Keep in mind that because these calculations are so similar, and you just have to remember a little bit, this takes a little bit of practice. So the calculations aren't hard per se. What's hard is getting used to switching between one type of circuit and the other kind of circuit. And also be careful when calculating equivalent resistance in parallel. That's the biggest mistake I see on for circuits. It's miscalculating the resistance. And if you miscalculate the resistance, a lot of other things can go wrong. So be careful and use a calculator and practice calculating these things. Another comparison that we can have, or another analogy we can have, is the traffic comparison, where resistors act like toll booths or construction. I don't like that analogy as much because not many students in the area I live in, there's not as many tolled roads. So not every student will have gone through a tollway. I prefer the obstacle course comparison because I feel like students will have run a race or gone around some sort of obstacle a little bit more than going through toll booths. This is a nice little summary of what happens in series and what happens in parallel. These are not, these diagrams for series and parallel are not complete circuits. They're just little sections of circuits. We would have to have some connections for the electricity to keep going in and going out. Notice that for current and voltage, in both cases, something stays the same, and in both cases, something changes, and they switch. So that's another reason why it can be a little confusing if you don't practice. Because if you don't practice, you'll have trouble remembering, oh, what do I do now? What stays the same? What's different? The more you practice this, the easier it'll become. These two equations are not, or this set of equations is not so useful for the actual calculations, especially the two that stay the same.